This is Professor Hill, and this is the second half of Geology, where we answer the question as to the mechanics of plate tectonics. In simple words, how does it happen? And then do a little on magnetics and a few other subjects. So, how do plates move? How do the plates move? The simple answer is convection. Convection of the mantle. Remember, the mantle is the next layer down underneath the lithosphere, and it's kind of a plasticky or jello-y type of version of the Earth, and it's capable of movement. Convection is the movement of a fluid, which the fluid is anything connected. It can be liquid, it can be air, it can be rock, as long as it's connected, and the movement by heat, because warm things rise and cool things sink. It's the same principle that we have for radiators. Not that we use radiators a lot here in the Southwest, but if you're ever around radiators, it's warm above them, and then the cool air sinks and is pulled back to the radiator. Or if you're ever standing on a fan, if you're ever standing on a ladder, checking out a fan, you'll notice it's a lot hotter on the top of the room than it is on the bottom. If you open an oven, does the warm air rise up and hit you in the face, or does it fall down and hit you on the feet? If you have one of those refrigerators with a freezer that's up above, when you open the freezer, does the cold air come down and hit you in the face, or does it rise up and go to the ceiling? Cold sinks and hot rises, because hot is less dense. Now, what we've got here is a really nice video, if I can get it to play. And I will be able to get it to play. Excuse me. Continue recording. Where a geologist with a really cool Scottish accent will kind of say the same thing, but he shows it to you with much better special effects than I have.
It happens because hot rock rises, heated by the Earth's core. Near the surface, the rock spreads in two directions and goes sideways. It begins to lose heat. Eventually, the much cooler rock sinks back down.
So this would be our mid-ocean spreading ridge.
Through this spreading process, the Earth's crust is very slowly dragged apart. And it's this that ultimately causes the continents to move. Where the plates collide, the rock on the seafloor containing carbon from the dead plankton is carried deep into the Earth. As it descends, this layer of rock is heated, so the rock melts, releasing carbon dioxide.
So this is subduction, right? This over here would be the oceanic trench, the deepest part of the ocean, and this is where the denser rock subducts under the continental crust. And this is that, I told you about 50, 60 miles away, that's where the volcanoes come up.
And gas is returned back into the atmosphere during an eruption. The remarkable cycle is complete.
Okay, it is a remarkable cycle. Now, I may not always show you all of the videos that I have.
Oh, he's my miracle child.
All the videos I have, because sometimes when I'm switching around, it messes up my recording. And then I have to do it all over again, which is very annoying. Okay, continental versus oceanic crust. Why do we call them that? Remember we talked before that the Earth has layers that are determined by density. Density is mass divided by volume. So, for example, I've got in my hand here a steel ball and a rock. They're about the same size, but the steel ball has much more mass, so it's much denser. If I were to drop these two objects into a bowl of Jell-O, the steel ball would sink down lower because it has more density. And that's what causes stratification of our planet. The different layers, the heaviest ones in the center, and they get lighter on the way out. But once we get to the outside, the crust, there are actually two different kinds of crust. So there's the one crust that is lighter that we call the continental crust. Lighter meaning less dense. And the heavier, more dense continental crust sinks down lower in the mantle, just like the steel ball would sink down lower in the Jell-O. So if we look at this picture, which is supposed to depict the planet without its oceans, you see the continents are sticking up because they're made of continental crust, which is lighter than the oceanic crust, which sinks down. And because it sinks down, it's the lowest place, and so that's where the oceans lie, is in the lowest place. Of course, water always goes to the lowest area. So that's why we call that type of rock oceanic crust. Okay, let's move on to another subject called magnetism. It's very important because without our magnetic field, we would not have life on this planet. So we have this cool magnetic field. It is invisible to us, but we can measure it. It's an electromagnetic field. It has an electrical component and a magnetic component. It comes out of the bottom of our planet, roughly, and it goes into the top of our planet. It's one of the four basic forces that I said were created about the first second after the Big Bang happened. It's one of the four basic forces. It's kind of like a battery. It's got a negative end and a positive end. The place where it comes out on the bottom of the planet is considered the negative end, and where it goes in the top of the planet is the positive end. It is not that strong as far as what we think of as strong magnetic fields. You know, the refrigerator magnets you have at home, if you have any, are about 1,000 times stronger than the magnetic field. But without our magnetic field, there would be no life on our planet, which without our refrigerator magnets wouldn't really matter, would it? The reason being is that our magnetic field diverts solar radiation around the planet. Again, I told you during cosmogony that the sun is essentially a nuclear fusion bomb. It's fusing hydrogens together to helium, and that creates a tremendous release of energy and all sorts of radiation. Some of it still gets through and can burn our skins if we're outside too long. But most of it is deflected around the planet. This picture here shows Earth, this little tiny Earth in the middle of these field lines, electromagnetic field lines, and you see they're being distorted by the solar radiation. Some, radiation does get through, especially at the top and the bottom. That's what causes the northern and southern lights. But most of it goes around. And it's not by coincidence that they believe our magnetic field evolved approximately 3.45 billion years ago, and that's about the same time that the earliest life showed up on our planet. If we didn't have one, the first thing that would happen would be the solar radiation would blast away our atmosphere. The second thing would happen, without the atmosphere, the oceans would boil away, and we'd be just left with dry rocks and sediments. I don't know even how long those would last. All right, so how is a magnetic field generated? You need to know this for the test, so remember these things. It has to be liquid, metal that's rotating. That generates the and that is created, and I should have this up here too, write it down. That is created by the outer core of our planet. The inner core is solid metal. The outer core is liquid. Later, well, no, I won't tell you, I don't think. If you take geology, you'll find out how we know that what's solid and what's liquid, but it doesn't really matter. We know that the outer core is liquid. It's the same idea as a generator in your car, which is a coil of metal that rotates and produces electricity. It's not liquid, but then it doesn't have to produce a planet-size electromagnetic field. Now this link I have down here on the bottom, I'm not going to show you this time because I tried to do it in the last time I recorded, and now I have to do it over again. but it shows a really kind of few minutes of a cool experiment where some scientists created a mini planet, and they made a liquid outer core and a solid metal inner core, and then they rotated it to see if they could generate an electromagnetic field. They could. Magnetic fields reverse. What we call normal is when the electric field comes out the bottom of the planet and goes in the top. When you take a compass out, the needle points in the direction that the magnetic field flows. For reasons that we do not understand, every so often in geologic time, it reverses. I think the last time was probably 700,000 years ago or something. And anyway, the field lines come out the top and go in the bottom every so often. And it doesn't just flip like that, you know, there's a transition period. But we do know it happens. It's part of the rock record. This line here is a recording for the last 4 million years. This is time over here in millions of years, 4 to present. These are geologic names of time, because geologists don't measure time in like millions of years. They have time periods of important geologic events, and they have names. And this line over here, the black and the white, or pink, is showing normal versus reversed polarity. So this is normal for us, right, is the black. And pink would be reversed. And so as you can see by looking through here, there's no pattern at all. It's statistically random, the reversals. There's no pattern. There's no pattern. And there's also no evidence that anything happens on the planet when this happens. There's no like tidal waves or extinction events or anything like that. Every so often you see something on the internet where they go, there's going to be a magnetic reversal and all these things are going to happen. There's no evidence that anything happens. So how do we know this? You know, if I said the last magnetic reversal was 780,000 years ago, there were no humans on the planet. So how do we know that? We know that through geology. There's a mineral called magnetite that is magnetic. It points in the direction of the magnetic field. So on spreading ridges, as the magma cools and the magnetite crystallizes out, it orients itself in the direction of the magnetic field. Now, this is also, you know, more evidence for spreading ridges. Spreading ridges, they come up, right? They solidify and they move apart because more magma is coming up. So on either side of a spreading ridge, and in this illustration, the brown rock is supposed to indicate normal polarity, goes south to north, and the blue rock is supposed to indicate reverse polarity, from north to south. So if it's spreading, the times are going to be the same if you go equal distances from the center, right? So these 1 million year marks are about the same distance apart from the center. These 2 million year marks are about the same distance. So you'll have the same kind of rocks. And so you notice here at this 2 million mark, it's going from normal to reversed. At this 2 million year mark, it's going from normal to reversed. And you see they match for the 3 and the 4 in this illustration. They match in real life too. Again, this was additional evidence to support the theory of plate tectonics. I believe, yes, you're going to do a lab on this. You're going to figure out rates of change given distances from the spreading ridge, the crest of the spreading ridge, and time. The times between them. This is the same thing, another picture of it. The high points are normal polarity, the low points are reverse polarity. This corresponds to this section of rock that's supposed to indicate a mid-ocean spreading ridge. There's the crack where the magma comes out, except down here they have positive for normal and negative for reversed. And again, you can see that there's lines that match as you go out because it's a spreading ridge. How are magnetic reversals useful to us? I don't know why I even have that in there. All right, I will see if I can put this in here this time. Last time I tried, it didn't work out. We'll see. Okay, this is supposed to be an illustration. It's a really nice little animation 5 million years to present. These are geologic names, you know, geologic names as opposed to the time. I'll hit this. The magma's coming up in the mid-ocean spreading ridge. The white indicates normal polarity rocks. The black indicates it reverses. You see the little compass needle over here? When it's black, it's normal, it's that way. When it reverses, if we were on the planet when the polarity reversed, our compass needles would point south. This also illustrates subduction, right? Here's a trench where it's subducting under the continental crust. And, you know, about 50, 60 miles inland, it melts and the lighter materials go up and creates strings of volcanoes. And again, notice that there's no pattern to the reversals. I've said that a bunch of times now, so it probably means it'll be on a test or something like that. All right, till next time.